Now we come towards the concept of motion in lift. Now when we speak of lift, now ordinarily lift is stationary. The object is placed on the surface or a person is standing on the surface of the lift. Then its weight mg will work downward and the reaction applied by the surface on the man, that will be R, it will be upward. So when the lift is not moving up or down, then normal reaction will be equal to weight of the body. So R is equal to mg. But when the lift is moving up, it means it is moving in the direction of R. Weight is downward, so we make an equation R minus mg equals to ma. And from this equation, we can get the value of R. So what is the equation? That is R minus mg is equal to ma, or R is equal to mg plus ma. M is taken out common and it will be g plus a. So it means that whenever the lift is moving up, acceleration is added to the value of g. But when the lift is coming down, it means it is coming in the direction of mg. So mg minus r will be equal to ma. So mg minus r means that mg minus ma is equal to r. So acceleration will be subtracted. But if the lift is stationary, we find r is equal to mg. Now, if lift is moving up with the constant velocity, then we will consider acceleration as 0. Again, we will come to the conclusion that r will be equal to mg. And similarly, when the lift is coming down with constant velocity, then again acceleration is 0. And finally, we reach to a solution r is equal to mg. Well, motion in a lift is now depicted like this. The weight of the body is simply the force exerted by earth on the body. If body is on accelerated platform, the body experiences fictitious force. So the weight of the body appears changed and this new weight is called apparent weight. Let a man of the weight W is equal to mg be standing in a lift. We consider the following cases. Now case 1, lift moving with constant velocity. So indirectly we are saying acceleration 0. It is shown in the figure, weight is mg. And if the lift is moving with constant velocity, upward or downward, acceleration will be 0. So normal reaction will be equal to mg. So weight can be taken as mg. In this case, there is no acceleration, hence no hidden force experienced by observer in the slide, and apparent weight W will be equal to actual weight. Now for case B, the lift is accelerated. The net force acting on the man are weight mg downward and fictitious force m0, that is ma downward, as shown in the figure. Now upward force is R is mg and downward is this one. So we will say that net force will be mg, that is R minus mg or W minus mg. And if we calculate it, it will become m into g plus a. Acceleration is upward and acceleration due to gravity is downward. So the apparent weight, that is W plus F naught, or W is equal to mg plus ma or m into g plus a. Effective gravitational acceleration is g plus a. So whenever body is moving up or lift is moving up, we will take acceleration added to g. C part, if the lift is accelerated downward, then in that case A is less than g. The fictitious force will be ma acting upward while weight acting downward, as shown in the figure. So again in this case, we will find W is equal to W dash will be W plus F naught, or it is mg minus ma or m into g minus a. So the point to understand is acceleration is subtracted from g. The effective gravitational acceleration will be g minus a. While going down, g minus a. While going up, g plus a. Special case. G will be a when W is 0. That is called the condition of weightlessness or free fall. Thus, in freely falling lift, the man will experience weightlessness. Now, case D, if the lift accelerates down with acceleration A greater than G, then as in case C, then we'll come to the following conclusions. W is m into G minus A or minus m into A minus G. So it is negative. The man will be accelerated upward and will stay at the ceiling of the lift as shown in the figure. Now we come towards certain examples of the elevator, that is lift. Mass of an elevator is given 500 kg. We have to calculate the tension in the cable of the elevator when the elevator is stationary. So R will be equal to mg, and ascending with acceleration, it means acceleration is to be added, and when it is coming down, the acceleration is to be subtracted. So now the solution will be force on the elevator is mg. So m is 500, g is 9.8, and the net value will become 4900 newtons. When the elevator is stationary, the acceleration is 0. The net force on it will be 0, that is figure A, that is T minus mg is equal to 0, or T is equal to mg, 4900 newton. That is the first case. In the second case, we find that the elevator is moving up. In the third case, elevator is moving down. Now, when the elevator is accelerated upward, the net force on it will be upward direction. So we have taken the equation that is T minus mg is equal to ma and T is equal to mg plus ma. The net value will become 5900 newtons. Now in the third case, elevator accelerated down. We use the equation mg minus T, that is equal to ma. Then we find T, that is mg minus ma, and it is calculated to be 3900 newtons. Now another example, the case of lift is again taken. The lift of mass 2000 kg is supported by a thick steel rope. If the maximum upward acceleration of lift is 1.2 meter per second square and the breaking stress for the rope is 2.8 10 to the power 8 Newton per meter square. That is what the elasticity given. What should be the minimum diameter of the rope, accepting G as 9.8. G, if given, we have to use that value, and if G is not given, we have to use the value 10 meters per second square. Now, when the lift is accelerated upward, the tension T in the rope is greater than the gravitational force, mg. Therefore, the equation is T is equal to m into g plus a. Mass of the lift is given 2000 kilogram. Acceleration is also given, and g is obviously 9.8. So we compute the value in the equation, and the exact result comes to be 22,000 newtons. If R is the radius of the rope, then stress is force over area, and force is tension here. Area of the string will be, or area of the rope will be pi r square. So from this, we get the value of T over pi r square by putting this value. And R square can be calculated, and R square comes to be 1 over 4 into 10 to the power 4. So from this equation, R is estimated, and it will be 0.005 meters. In the another example, again, a case of lift is taken. A lift is going up. The total mass of the lift and the passenger is 1500 kilogram. So lift and passenger will constitute a system. The variation in speed of the lift as shown in the figure. What will be the tension in the rope pulling the lift at 1 second, after 6 seconds, and after 11 seconds. So the curve is indicated here. On the y-axis, the velocity in meters per second is taken, and on the x-axis, the time is taken. So now, according to the question, we find the slope of VT curve is acceleration. Therefore, at t is equal to 1 second, acceleration, that is final velocity minus initial velocity divided by 2, and that comes to be 1.8 meter per second square. Lift is moving up. We use the formula T is equal to m into g plus a. We compute the values, and the estimated value is 17,400 newtons. But at t is equal to 6 seconds, A will be 0, t is equal to mg is equal to 1500 into 9.8, that is 14,700 newtons. At t is equal to 11 seconds, again the same calculations are carried out, and we find that the value we compute will be 0 minus 3.6 by 2. That is, the formula of acceleration is v minus u over t. So it is a negative one, that is minus 1.8 meter per second square, being the lift is moving down. So we use the formula t is equal to m into g minus a. It's not mg, rather it should be m into g minus a. So we put the value, that is 1500 into 9.8 minus 1.8, and this value comes to be 12,000 newtons. The figure is again depicting the third case also.